This is 40 Days of Chemistry, Part 18, at this time looking at ozone and CFCs. Just as a quick recap, the first thing we do in this topic is look at the structure of the atmosphere. We then move on to what is ozone and where is it and how does it work. We compare the chemistry of ozone to oxygen and oxygen-free radicals. We look at how CFCs have damaged the ozone layer. We then look at what are we doing to monitor it, and also what are some of the possible solutions to the damage we have done. So first thing, what is the structure of the atmosphere? The atmosphere comes in layers. The lowest layer closest to us is the troposphere. Then comes the stratosphere, the mesosphere, the thermosphere, and don't forget the ozone layer is in the stratosphere. And what's the ozone layer do? Well, what it does is it blocks UV light. So all the colours of light coming from the sun, UV light hits the ozone layer, and the amount of UV light reaching the Earth's surface is decreased because of the ozone layer. And how does it do it? Well, the ozone layer consists of an equilibrium between oxygen, oxygen-free radicals, and ozone. Oxygen molecules themselves can absorb UV light, breaking down into oxygen-free radicals. Oxygen-free radicals can then react with oxygen molecules to produce ozone, and ozone can absorb UV light, breaking back down to oxygen and oxygen-free radicals. That's why we say ozone is good up high in the stratosphere, because it absorbs dangerous UV light. We know that UV light causes skin cancer and other effects. But ozone, in fact, is bad nearby. It's actually bad in the troposphere. In the troposphere, it's toxic to life. It's a highly reactive chemical. It's dangerous to plants and animals. And one of the main sources of tropospheric ozone is nitrogen dioxide coming from car exhaust or combustion engines. And nitrogen dioxide, when it's hit by light, breaks down to nitrogen monoxide and oxygen-free radicals. Those oxygen-free radicals then react with oxygen molecules in the troposphere, producing ozone, which we know as smog. We also looked at some other pollutants in the atmosphere. We looked at lead, we looked at nitrogen oxides, sulfur oxides, carbon monoxide, carbon soot, and carbon dioxide in this topic too as pollutants. We study each of those in more detail in other focus areas. The next thing we looked at was the actual chemistry of the ozone molecule itself. And we started off just by looking at oxygen atoms, single oxygen atoms. Now, single oxygen atoms in their outer shell have 6 electrons in the outer shell, which is an incomplete outer shell, and they've got 2 unpaired electrons. And any species with an unpaired electron is called a free radical. So an oxygen atom is called an oxygen-free radical. And free radicals are very reactive. Their electrons want to form bonds to complete their outer shell, but also so they're paired up. And therefore, you can't actually measure the melting point and boiling point of oxygen-free radicals, because if you try and put more than one together, they'll just bond to form oxygen molecules. Now, oxygen molecules is the most common form of oxygen, or the most common allotrope of oxygen in the troposphere. It's the oxygen that we breathe that's useful for life. It consists of 2 oxygen atoms joined by a double covalent bond, and it's a non-polar covalent molecular substance. However, if an oxygen molecule encounters an oxygen-free radical, then what you'll form is an ozone molecule, an O3 molecule. The oxygen-free radical joins on to the oxygen molecule by a process of formation of a coordinate covalent bond. And don't forget, that's a covalent bond where both electrons have been donated by the same atom, as opposed to a normal covalent bond where one electron comes from each species. Now, a coordinate covalent bond is exactly the same as a normal covalent bond, apart from the fact that both electrons have come from the one atom. 2 other species that we know of that have coordinate covalent bonds are the hydronium molecule and the ammonium molecule. Now, what are the differences between these allotropes of oxygen and ozone? Well, first of all, oxygen's clear, whereas ozone's pale blue. Their similarities are they're both covalent molecular, so therefore their melting points are low and their boiling points are low. However, they are different, their melting points and boiling points. Oxygen molecules, as we said, are non-polar, therefore they've got the lowest melting point and boiling point out of these 2, whereas ozone molecules are slightly polar. And that's because this central oxygen atom is actually sharing electrons with 2 other atoms, whereas each of these oxygens on the side only share electrons with 1. And if you count up how many electrons each one has, I suppose, the one here's got 6, this one's got 5, this one's got 7. This makes this end of the molecule slightly negative, this end of the molecule slightly positive. So ozone, even though it's only got the same types of atom, it is a slightly polar molecule because of its bent shape. Because it's slightly polar, it's got slightly higher water solubility than oxygen, because water is a polar solvent. The polarity makes it have a higher boiling point and melting point than oxygen, but also the very fact that it's heavier, having 3 atoms rather than 2, means it's got a higher melting point and boiling point because it takes more energy to vibrate. Now, CFCs are the chemicals that are damaging the ozone layer. They were used for refrigerants and aerosols because they were non-toxic, non-flammable and stable. They were thought to be perfect replacements for dangerous chemicals like ammonia in refrigerants. And in the troposphere they were fine, they caused no problems at all. But it was their very stability that ended up causing the problems, because what happened was they started diffusing upwards through the troposphere and they reached the stratosphere. And it was in the stratosphere they were first encountered by ultraviolet light. That's because the ozone layer was luckily for us blocking the UV light. It didn't reach the troposphere, but once it reached the stratosphere, these CFCs, UV light started to strike these molecules, and UV light can decompose these molecules. And one example here is chlorotrifluoromethane. It was called Freon 13 or CFC 13. It was used as a refrigerant. And if that reached the stratosphere past the ozone layer with those UV light, the UV light would break that down into a free radical here and a chlorine free radical. And it's the chlorine free radical that causes the damage to the ozone layer, because chlorine free radicals react with ozone molecules to produce chlorine monoxide and oxygen molecules. That chlorine monoxide can then react with oxygen free radicals in the ozone layer, because we know that part of the equilibrium. That reforms the chlorine free radical and produces oxygen. And that chlorine that's reformed, that chlorine free radical that's been reformed here, can then go back and react with another ozone molecule. So we say that chlorine free radicals are a catalyst for ozone decomposition. It's a good sentence to use if you're talking about the ozone layer and CFCs. Now, one chlorine free radical will destroy about 10,000 ozone molecules before it is stopped by a reaction in one of these two reactions. It either reacts with nitrogen dioxide in the atmosphere or methane in the atmosphere, and that stops that chlorine free radical chain and produces these two things, chlorine nitrate or hydrochloric acid. And that leads us to, what's the difference between ozone depletion and the ozone hole? Well, we know that naturally there's this ozone equilibrium in the atmosphere. We also know that the CFCs we produce chlorine free radicals which destroy or decompose ozone, and that's ozone depletion. That happens globally. CFCs decompose ozone globally. We also learned that there's these two terminating reactions that stop that process, but they produce chlorine nitrate and hydrochloric acid. And it's these two chemicals that contribute to something called the ozone hole. And the ozone hole only forms over Antarctica, although a small one's starting to form over the Arctic, and it only happens in early spring. So why does that happen? Well, in winter in the Antarctic, it's dark and it's cold, and there's a special sort of wind called the polar vortex, and that causes these two chemicals, chlorine nitrate and hydrochloric acid, to concentrate above Antarctica. And because it's so cold there, special ice crystals form in the stratosphere, and these ice crystals are catalysts for the reaction between hydrochloric acid and chlorine nitrate, and that process actually causes molecular chlorine, or CO2, to form. Now, molecular chlorine is harmless to the ozone layer. It has no effect, and it builds up in concentration in winter. But then when spring comes around and UV light returns, the UV light actually splits these chlorine molecules up into chlorine-free radicals, and you get a sudden cascade of chlorine-free radicals above Antarctica in early spring, and that leads to rapid decomposition of the ozone layer to form the ozone hole by these reactions we studied earlier. Now, by summer, the chlorine-free radical concentrations drop because it's been reacted out again. You get mixing of air from the rest of the atmosphere, so the hole closes, but that's why the ozone hole forms in spring over the Antarctic. So what are we going to do about this CFC problem? Well, CFCs, as we know, are chlorofluorocarbons containing chlorine, fluorine, and carbon, and they are very damaging to the ozone layer. Another class of chemicals called halons, which are like CFCs but contain bromine, are much worse for ozone decomposition. But what they've done is they've decided to replace them with hydrochlorofluorocarbons, or HCFCs. They contain hydrogen as well, and that makes them more reactive, more likely to decompose in the troposphere and not make it to the stratosphere. But because they do contain chlorine, they do have some ozone depletion potential. It's less than CFCs, but they do have some ozone depletion potential. So the next stage in the replacements is going to HFCs, hydrofluorocarbons. They have no chlorine and no ozone depletion potential. The only problem with HCFCs and HFCs is they've got a high global warming potential. They're more expensive to use sometimes than CFCs and require modifications of equipment. But they don't damage the ozone layer as much, or they don't damage the ozone layer at all in the case of HFCs. And it's the Montreal Protocol, which is the international agreement to phase out CFCs in favour of HCFCs and then HFCs. It was signed in 1987. CFCs were phased out between 1989 and 1996, and HCFCs have been phased out between 1996 and 2030. In actual fact, 2013 this year is the freeze in HCFC production, and as of 2015 we're supposed to be reducing our HCFC production in favour of HFCs. But how do we know how much damage has been done to the ozone layer, and how do we monitor whether our techniques to try and solve the problem have been working? Well, that's done through ozone monitoring, hence it's in the chemical monitoring and management topic. We want to monitor ozone depletion so we know how the problem is going. We want to monitor ozone so we can predict the UV index. And we also want to monitor ozone so we can see have things like the Montreal Protocol have been having a positive effect on the ozone layer. Can we fix this ozone layer? And there's three main ways we can monitor ozone. It's through Dobson spectrophotometers. They sit on the surface and they monitor ozone above a local spot only on the Earth's surface. They do that by monitoring a wavelength of light that ozone does and doesn't absorb to figure out the ozone concentration above the Dobson spectrometer. They've also got weather balloons. They're released from the surface and travel up through the atmosphere based on the weather. They're only local measurements and they are controlled by the weather, but they provide useful information because they make an altitude versus ozone concentration plot so we can see what altitude the ozone is at. Satellite monitoring is probably the most advanced and most effective monitoring of the ozone layer, though. It's monitored by recording wavelengths of light that ozone scatters or reflects back into space. There's been a range of satellite instruments that measure ozone. The current one is the Suomi NPP satellite, which is carrying the OMPS or OMPS, which is the Ozone Mapper Profiler Suite. And that takes global measurements of ozone. So anytime you see maps of the ozone layer or the ozone hole, they've been taken by satellites because they've got what's called polar orbits. They orbit from north to south pole and the Earth spins underneath them, so they can take measurements of the entire globe's ozone layer. And this particular satellite, this new one, the Ozone Mapper Profiler Suite, the reason it's called a Profiler Suite is because just like the weather balloons, it can figure out, as shown in this diagram down here, the ozone concentration at different altitudes. The way they measure ozone is a Dobson unit or a DU. 1 DU is equivalent to 0.01 millimeters of pure ozone at 100 kilopascals and 0 degrees. So if you brought the ozone down to Earth's surface and cooled it down to 0 degrees, how thick would that ozone be? And the ozone layer is typically only 300 DU or 3 millimeters thick according to that scale, so it's quite fragile as you can imagine. The last thing we did in this topic was naming haloalkanes, and I think we mastered most of the haloalkane naming tricks. You got things like you got to make sure you number which carbon the halogen's on. You put hyphens or dashes between numbers and letters. If you've got more than one of a particular halogen, you use these prefixes like di, tri, and tetra, and you also indicate which carbons they're on by using numbers. But between numbers, you put commas. At the end, after naming all the halogens, and don't forget you name them in order: bromo, chloro, fluoro, and iodo if you have to. You name the alkane chain, in this case propane, because there are 3 carbons. But the one big trick, the one that was wrong in the HSC last year, is the numbering system if there's 2 equivalent numbering systems. So you know you've got to check the numbering from both ends of the molecule. If both numbering systems are the same, you number from the end that gives the first alphabetical halogen, so bromine in preference to chlorine in preference to fluorine, that gives that first alphabetical halogen the lowest possible first number, or using technical terms, the lowest locant. Locant being these numbers because they locate where these halogens are. So in this case, the correct numbering for this, the correct naming of this molecule would be 1 bromo, 1 3-dichloro, 2 3-difluoropropane. You have to number from this end because that gives bromine, the first alphabetical halogen, the lowest locant, which is 1. And that's the end of this talk. Our next talk will probably be on indicators or esters.